Hello, everyone, and welcome to our Research Trends in AI breakout session, exploring some of the latest research in AI from Vector faculty and faculty affiliates. My name is Ethan Jackson, and I am a technical AI staff scientist at the Vector Institute and your facilitator for this session. For the Q&A today, please private message your questions to the user named please send your questions here using private message, and we will try to get through as many questions as possible. The first speaker for today is Nicolas Papernot. Nicolas is an assistant professor at the Department of Electrical and Computer Engineering and the Department of Computer Science at the University of Toronto. He is also a faculty member at the Vector Institute, where he is a Canada CFAR AI chair and a faculty affiliate at the Schwartz-Reisman Institute. His research interests span the security and privacy of machine learning. Nicolas is a CONUT researcher and was previously a Google PhD fellow. His work on differentially private machine learning received a Best Paper Award at iClear 2017. He serves on the program committees of several conferences, including ACM, CCS, IEEE, S&P, and Usenix Security. He is also the co-author of CleverHands and TensorFlow Privacy, two open source libraries widely adopted in the technical community to benchmark the security and privacy of machine learning. He earned his PhD at Pennsylvania State University, working with Professor Patrick McDaniel. Upon graduating, he spent a year as a research scientist at Google Brain in Wolfar Erlingson's group. Please welcome Nicolas Papernot, who will be speaking on security and privacy.
Thank you, Ethan, for the introduction. Can we go to the first slide? I guess the second slide directly might make sense. Yeah, can you skip to the next slide? So in here, I want to first introduce sort of what I mean by security and privacy in machine learning. And I think the broader question is essentially to think about what it means for us as humans to trust the predictions that machine learning is making. So I have two examples here that have been sort of demonstrated on real world systems of sort of failures of machine learning models. On the left is an example of a data poisoning attack where the adversaries are manipulating the data that the machine learning model is learning from. And in particular, what happened here is that Microsoft released a chatbot called Tay that was designed to learn from its interactions with Twitter users. And very quickly, users found that they could teach it how to produce racist and inappropriate content by just tweeting at it, and the language model would learn from these examples and produce similar ones afterwards. And here is an example on the slide of a tweet that the bot produced, one of the few that I was comfortable putting on the slides. On the right, I give an example of what happens, for instance, when you use machine learning on domains that have very high dimensionality. So for instance, YouTube uses machine learning to filter videos that are potentially inappropriate. And some parents found that some of the videos still made it through the filter in the YouTube Kids app, which shows that it's really difficult to capture the input domain when it has such a complex task, like in what is often the case in video domains. Can we go to the next slide? And so the question in terms of security is to understand how likely it is for an adversary to systematically find these inputs that the model is going to misclassify. And so here we've done a lot of research on that, and here I'm going to just quickly give an overview of the algorithm that we use to find these inputs without going into too much details. But essentially, the idea is to look at the architecture, the model that we're trying to attack, and compute its sensitivity to different changes of its input perturbations. And so the way that we do this is by computing gradients, just like we do compute gradients in training to minimize our objective. Here, we're computing gradients to instead maximize the mistakes that the model is making. And so instead of optimizing with respect to the model parameters, we optimize with respect to the input features. And so that allows us to compute what we call saliency maps that tell us how likely it is that the model will make the wrong prediction that the adversary wants the model to make if we modify each of the features of the input. And so if you go to the next slide, what we found with this algorithm is that we're able to systematically choose the mistakes that the model is making. Here, what you see on the diagonal is a series of correctly classified inputs, so from 0 to 9 on the diagonal. And every image outside of the diagonal is misclassified by the model in the in the class that is indicated by the label at the top of the column. So what this means here is that the model that was originally very good at recognizing digits that are found in these images is now classifying the first row as images being 0, 1, 2, 3, 4, 5, all the way to 9. So what this means is the adversary can essentially arbitrarily control the prediction that the model is making by just introducing these perturbations to the inputs. And so here, as you go to more complex tasks, so I just mentioned sort of videos and so on, the perturbations become very hard to notice to humans. They don't really alter the semantics of the input. If we can go to the next slide, what I'm illustrating there is that in terms of the safety of systems that deploy machine learning models, this has a lot of implications. And in fact, people have started doing research demonstrating that, for instance, changes of lighting in the input of self-driving car platforms can lead them to take drastically different actions in terms of the driving. And so you can see that even when there is no adversary worst case examples, the implications for safety are still there, where you want the model, you want to understand how your model will perform in the worst case. If we go to the next slide, I want to switch gears and talk about the second topic that I mentioned in the title of this talk, which is privacy. So here the idea is to say, if we train our machine learning models on data sets that are sensitive, so that includes, for instance, medical records, then essentially what the adversary might be, could we switch to the next slide, please? Then the adversary would be able to observe the model's predictions and from this infer whether a particular point was included to train the model or not. So for instance, if you're training a model on healthcare data, being part of the training set might leak a lot of private information and you might not want to be revealing this information. And so unfortunately, what we found is that in our attacks, we're able to infer this membership even if we only have access to the label predicted by the model. So if we go to the next slide, part of our research efforts have been coming up with algorithms that protect the privacy of training points that we learn from when training our models. And so the way that we're doing this here at a very high level is to, rather than train a single model on the entire sensitive data set, we train an ensemble of models trained on subsets of this data set. And we allow them to predict only when they have a strong consensus among these models. And what this means is essentially that the predictions are private when we are able to make sure that we can make this prediction multiple times independently from these different models in the ensemble. And it's also more likely to be correct because, again, we made this prediction independently. So what this means is that the model is generalizing well. So this is an approach called pâté. There are other approaches to obtain privacy. And here, one of the advantages is we're getting guarantees in a framework known as differential privacy, which means that we have very strong guarantees that hold even if the adversary has access to auxiliary sets of data, which is one of the sort of the limitations of other approaches like anonymization or trying to de-identify data, which is always vulnerable to linkage attacks. Here, this approach is not vulnerable to any of these attacks because it doesn't make any assumptions about the knowledge of the adversary. So if we go to the next slide, I think the sort of the overall goal that we're trying to pursue as a lab here at Vector and UFT is to try and align machine learning with human norms at training time, which is going to allow us to increase the trust that humans have in the model's predictions. This is an open problem in particular when you try to combine different guarantees. So if you want to align, for instance, machine learning with both expectations of security and also of privacy, then this creates new challenges that you wouldn't face if you were just trying to obtain privacy or just trying to obtain security. One last comment before I conclude on the next slide is that a lot of these problems raise open questions that cannot only be addressed by technology. So for instance, we've worked on deepfakes recently, and what we found is that there is an inherent limit to what we can do with technology in order to, for instance, detect deepfakes, because the technology itself with things like generative adversarial networks is designed to interact with any detector that we may come up with. So we won't be able to, for instance, solve the problem of deepfakes by coming up with a machine learning detector for deepfakes. Instead here, what is very clear is that we have to come up with hybrid solutions that involve both sort of technology approaches, but also policy-based approaches with new legislation or more ethics education for engineers, for instance. So with this, I'll conclude with the last slide saying that I think trustworthy machine learning is really an opportunity to make machine learning better, in the sense of, if we look at some of our results on privacy, what we found is that by making the models more private, we get better guarantees for these models in terms of the generalization as well. So this is really an exciting time, because we're still developing these technologies, and we can not only make them very accurate in the sense that they make the correct prediction, but we can also align them better with what we as humans expect these models to do. So this is something that I'm discussing more on my blog, cleverhans.io, if you're interested in more details. With this, I'll leave the floor to the next speaker.
Great. Thank you very much, Nicolas. We do have time for one quick question from the group. So one user is asking, does federated learning have application along with differential privacy?
So federated learning is not a privacy preserving mechanism. So federated learning basically means that rather than sharing the data to the central party training the model, we're sharing gradients. But the gradients still contain the private information. So the privacy leakage is still happening in federated learning. It's just really an approach for decentralized training. It provides no guarantees of privacy in the sense of differential privacy.
Great, thank you. There are more questions. We'll see how much time we have at the end of the session to continue. Thank you very much, Nicolas.
Yeah, my pleasure.
Great. All right, so the next speaker in this session is Parvin Musavi. Parvin is a professor of computer science, electrical and computer engineering, and pathology and molecular medicine at Queen's University, and a member of the Royal Society of Canada. She received her PhD in electrical and computer engineering from UBC. Previously, she had held industrial positions and visiting professorships at Harvard Medical School and UBC. Her research interests are in machine learning applied to oncology, computer-assisted interventions, and neurology. She has received over 40 international and national recognitions for research and has led numerous multinational collaborative initiatives in these areas. Parvin represented the Royal Society of Canada in the summit of the G7 Academy of Sciences on the topic of AI in society. She serves on and chairs several national and international granting committees. She is the General Chair of Information Processing in Computer-Assisted Interventions, IPCAI, on the Executive Board of Medical Image Computing and Computer-Assisted Interventions, MICAI 2020 and 2023, and a founding member of Women in MICAI. Please join me in welcoming Parvin, who will be presenting From Inception to Clinical Translation of Learning Models in Computer-Assisted Medical Interventions. Parvin?
Thank you very much, Ethan. I'll just, thank you for going through the trouble of reading that entire introduction. Okay, thank you for the opportunity, and I'm honored and delighted to be here speaking to students that are attending and other colleagues that are attending the session. So the governments of G7 in 2020 have released a letter. They have multiple focus areas that they work on, actually several years before the year itself. And it happened in 2020 to be digital health and learning health systems. These letters are all public and you can take a look at it. It also coincided with the pandemic that is changing our lives and will change how history is written and how we interact with health systems forever moving forward. In that letter, there are multiple things that are emphasized, but I want to emphasize three things, and then I want to walk you through examples of some of these topics that were brought up. Analytics, technology, and security are important, not just in the learning systems that we are building, but also in data and education of not just the technical societies and students and academics and people in industry, but the population on these issues. the existence and security of reliable data to build these kinds of learning systems, so learning health systems. And then finally, thinking about the fundamental question of who benefits from these technologies that we are building and how should they access it. So access shouldn't be for one, access should be global. And fortunately and unfortunately, the pandemic has made many of these topics very important and something that we all can relate to. The trend of AI has been exponential, not just in general, but in healthcare, in particular, imaging and diagnostics. You can see from my statistics from 2020 to 2019. In addition to that, the way we access data in medicine, as well as the type of data we have access to, has changed. So whereas we had difficult data to quantize, to access and to record, now we have many sensors and types of data that we have access to. These are imaging sensors, sensors and interventions, in surgeries, electronic health records, and all sorts of other complementary sources. But what we are moving towards, and it's not really the future, it's now faster than the future, is connection between all of these important topics and data sources. So a single patient having information on many types of data that we have for that single patient. All of you have heard of the data, or may have heard of the data that the government of Ontario, Health Ontario, is releasing. It is in response to COVID, but starting to bring out a lot of the important issues, the types of data we have, and the need for essentially improving how we access, we connect, and we use that data. So in addition to that, we have both sensationalized and realistic advantages that we have with the algorithms that we are developing. So the question becomes, what are some of the challenges in the uptake of the technologies that we have in this field? A couple of things to think about. The data we are dealing with is limited, noisy, and imperfect. There's a variety of sensors, the quality of the sensors, the quality of noise, signal to noise ratios, the training of the operators that are taking this. So I have an example of a cart-based ultrasound system that takes images of, let's say, internal organs in this case, with maybe an operator that sees thousands of patients a year, so highly trained, versus a small device with high noise and the less trained operator. Another thing which is inherent is that pathologies, so disease and biology and their interaction is very heterogeneous. So in fact, a malignant image of a cancer, here is prostate cancer, has many forms to come. So 3 examples quickly of how we deal with these challenges and address them, and things that we should be aware of. This is work in progress. One has to do with detection of cancer, next one, treatment of cancer, and the third one, democratization of access to some of the technologies. So in diagnosis, my example focuses on prostate cancer, which is one of the most prevalent cancers in men worldwide. The diagnosis ultimately is biopsying the prostate with ultrasound guidance. Ultrasound is not specific, meaning that you can't see cancer necessarily with ultrasound. Therefore, it's just a guide. It's like a GPS system. So our innovations are on 2 fronts. First, improving the image information that you're able to see. You can use other modalities than ultrasound, or in our case, we have taken many more samples of the same location of the disease that one is looking at over time and analyzing this. So innovations in technology, innovations in sensor acquisition, and then deep learning. As an output, you have color maps that are overlaid in real time on the ultrasound. Here you see colors that essentially tell you that there's a variety of disease here, and this is a probability map and helps the guidance of biopsies. In addition to telling where cancer is, probably the clinician is interested to know how aggressive it is. And I want to take your attention to one of these pictures. These are pictures of 4 patients in one of our trials. A sample was taken from this particular point. You see that the probability map shows heterogeneity of outcomes. And actually, they took 2 two samples. The outcome of these two samples, one was that the cancer is not aggressive. The second one is it's very aggressive. So if one image was taken only one target, and if there was no heterogeneity in outcomes, then this patient might have been under wait and see, whereas they actually needed an intervention right away. Another issue, as I mentioned, is that our labels are really noisy themselves. So when a biopsy is taken from the prostate, there is a large amount of the data, imaging data, sensor data that we have, but the label for that is one label, very noisy and weak. So instead of using traditionally supervised methods or methods that rely on reliable, strong labels, what we are thinking about is that if we have labels and small parts of the image that we are sure about or more sure about than the rest of the image, instead of thinking about using all of our labels, we think about measuring similarity of the rest of the organ with these reliable labels and think about that. So instead of having cancer probability maps, we have tissue similarity maps and try and provide some guidance to clinicians that way. Finally, we don't have enough data. Thousands of patients, even if we are lucky, is not enough data, especially when we are dealing with deep learning architectures and methods. What we have a lot of is the knowledge of how images are created. So what we did was we took advantage of this. We know how ultrasound is created. It's the interaction of ultrasound signals with scatterers, which are cells in the body. We have a lot of pathology images. What if we were to take these images, quantize, segment these cells, and then put these cells in structures in simulation that mimic what the prostate of that patient, the distribution of cells in the prostate of that patient would have been like, and create ultrasound images with that. Based on those images, then we can use it to pre-train our models, we can use it in transfer learning model, and so forth, and create these maps based now on hundreds of thousands of cases that we can historically access. Second example, quickly, is on the treatment of cancer and the role of our learning and the approaches we should take given the challenges. This is for one of the treatments of cancer, the determinant treatments of cancer, especially in solid tumors, is surgery. Same for breast cancer. Ideally, you want all the cancers to be removed and you want healthy cells also to be removed, so negative margins. But in reality, for breast cancer, sometimes 1 in 4 women, sometimes a lot more than that, come back for surgeries, for second, third, sometimes fourth surgeries to remove all the cancer. You can imagine all the repercussions, both to the health system, to the patient, to their outcome, and psychologically of all of that. What if we had the ability in real time, while the patient is resecting the tumor, to tell the surgeon where they are and what kind of cell they are cutting through? So we do exactly have this technology. It is a knife, it's a knife, intelligent knife, that essentially takes the smoke from the cautery tip while resectioning the tumor or the tissue, suctions it, ionizes it, and you're looking at the mass to charge ratio through mass spectrometry of metabolites. So if we had models that learned what metabolites were specific to cancer cells, you could see that right now here, there's feedback to the surgeon that says that, I think you're cutting through tumor. So they would go back and scoop some more. The data is very noisy. The head of the cautery tip destroys, it burns. Therefore, you don't have labels. Your labels are guessing what it should have been from the surrounding, and it's quite noisy because it is essentially large. So again, we have to think about methods that are specific to noisy labels and mixed data. So multi-sense learning was one of the methodologies we learned. At the end, what you have is this, that a signal is coming through the machine, and when it is cutting through cancerous cells, that you have either a beep, a red color, something augmenting the surgeon's ability to know where they're cutting. We have actually done some intraoperative deployment of this technology. In addition to this knife, we have other technologies that complement it. We can track exactly where the surgeon is cutting through with the coordinate systems of the patient. We have preoperative images. In this case, for breast cancer, we have mammograms and ultrasounds. before the patient is cut, so before the resection starts. And we can, as you see in this picture, show to the surgeon where the tool is with respect to tumor boundaries they took from ultrasound just before they started resecting the patient. So as they get close to this, they have two sources of information. They see their mass spec information from the libraries and the learning systems, and they have tracked devices that are telling them that you're very close to the tumor here. Finally, how do you democratize some of these technologies you build? The example here is from heart disease. It is from a group of very close collaborators at UBC. Heart disease is a disease that is prevalent, especially in older adults worldwide. It doesn't matter which country you live in or which continent you are. One of the most important modalities in assessing heart disease is ultrasound echo. It is harmless, accessible, cost-effective. But as I showed you earlier in my first slide, there's a variety of devices as well as training of the operators that makes the difference. So we want to make this essentially accessible to everyone, regardless of what their budgets are in terms of countries for infrastructure, or even within our own country, different places, rural, urban, with a lot of patient flow and not as much. A decade, tens of thousands of data from Vancouver Coastal Health was taken with deep learning models. And the outcome is this, that based on high quality images from devices that have very high signal to noise ratio, they were able to predict the quality of an image when it's taken. So here you see the green and light here. As the operator is taking the image, they have real-time feedback whether their image is high quality or low. So operators with less experience can train themselves. In addition, you can take high quality images and improve the quality of those images that come from noisy devices. So I want to thank hundreds of students, collaborators, patients, and of course funding sources that have contributed over the years to some of these projects. Thank you.
Parvin, thank you so much for this amazing presentation. We have time for one quick question from the audience. Someone is asking, what method did you use to convert the pathology images to ultrasound images, and how did it simulate noise that is characteristic of the ultrasound modality?
That's an excellent question. Unfortunately, not very short answer to that, but there are multiple methodologies that we use. So the first step is to essentially segment these cells out of the pathology images. Once you have a distribution of cells, you make an assumption that they are the scatterers. Then you have to create models, physical, mechanical models of what a human tissue would look like, how much it will be stiff, what its viscosity would be. And then you put these scatterers in this, and there are ultrasound simulation softwares that essentially take these scatterers you have with the biomechanical models that you have, and you create over time ultrasound images. That the noise question is a very important question. Unfortunately, the existing models that exist for ultrasound simulation do not simulate noise very well. It's difficult and very time-consuming to do ultrasound simulations. Therefore, your noise models are something you have to think about afterwards, and you have to do some work on yourself from the data that you have to try and mimic perhaps realistic noise that you get from your patients. From your patient populations. If I look at the message, I can maybe refer you to one of our papers that talks about this in detail.
We'll be sure to forward that to you. Thank you so much, Parvin. Great, let's go to our third talk. And this will be from Juan Felipe Carrasquilla, who's faculty member, Vector Institute, adjunct assistant professor in the Faculty of Science, Department of Physics and Astronomy at the University of Waterloo, and Canada CFAR AI chair. And I'll hand it over to you, Juan.
Yeah, thank you for the kind introduction. Let me share my slides. So my talk is about quantum matter research in the AI era. let me first get started by explaining what quantum matter is. It basically refers to a study of multi-particle systems whose description is intrinsically quantum mechanical. It falls into the field of condensed matter physics, but it has strong connections and cross-fertilization with other fields, such as quantum information, computational physics, quantum gravity, and many more. And this field is important for a few reasons. So one of them is it helps us develop technologies such as quantum computers, quantum devices. It helps us developing techniques to solve problems in quantum chemistry, chemical engineering, material science. And lastly, it helps us kind of like have a better understanding about how the universe works, right? Like, so it brings ideas from many fields, and more recently from machine learning, as I highlight here in my plot. And so what is this thing? Why is this happening, right? Like, so there's a recent resurgence in the condensed matter, quantum information, statistical physics, and atomic physics communities, where people are currently exploring research at the intersection between machine learning and quantum physics. And the origin of this resurgence is basically due in part to the success of deep learning in computer vision and natural language processing and reinforcement learning. This success, or this resurgence, is shaped in part by the commonalities in the structure of the problems that these seemingly related fields attack, so mainly machine learning and quantum physics, or quantum many-body physics. And so what I want to discuss today with you quickly is what are these commonalities, and are they even important beyond mere resemblance? And my goal is to try to convince you that these commonalities are important, and that we can use techniques borrowed from machine learning and for us to try to be able to make progress in our field, right? And so I'll provide a couple of examples and some applications. So what are these commonalities? So one of them, and one of the most obvious ones, is high dimensionality, right? Like, so imagine you have a camera, like the one in your phone, and you ask the question, how many pictures can a camera take? Is it millions or is it trillions? And so I'm going to explain this with a very simple example. So you consider a simple camera with L by L pixels. The camera can only take binary images, so each pixel can be either 0 or 1, or on and off. And so you see this type of images here. It's like, I don't know, like this puppet here, and this is represented by this digits here, where 0 is white and 1 is black. And so you can ask the question, how many different pictures can I get out of this camera, right? And so you can count this, and it turns out it's too many, but let me explain how you get there. So you take, I don't know, the first pixel can be either 1 or 0. That's 2 different values. Or then the second pixel can be either 0 or 1. And so when you combine 2 pixels, you'll have combinations of, I don't know, 0, 0, 1, 0, 0, 1, and 1, 1. Now you add a third pixel, and then you start combining more digits. So you have 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and so on. So if you count how many combinations that is, it's 2 to the third possible combinations. And if you go with 4, then you see that the number of possible pictures this camera can take is growing really fast. So you go from 0, 0, 0, 0, 0, 0, 1, and so on. And then there are 2 to the 4 combinations. And when you keep doing this game, you will find that for an L by L camera, with a camera with L by L number of pixels, then you get a number of pictures that is 2 to the L by L, okay? So the space of possible images is growing exponentially. And so if you take, say, for instance, 28 by 28 binary images, then you get a number of pictures that is 2 to the 28 by 28, which is this gigantic number, right? Like, and so this number is bigger than the number of atoms in the known universe, but luckily, most images are basically noise, and only a tiny fraction of this huge space correspond to meaningful images that our brain can process and that our brain understand. And so what we say, or what people in machine learning say, is that these images that our brain understands live in a low dimensional manifold that lives inside this big space. And I have this tiny example here in 3D where like this noise that is outside this manifold, which is represented by this blue curve of meaningful images, in this case, images of the digit 3, is what our brain understands that what we're interested in. And so how is this related to physics and statistical mechanics? Is like when we study this like physical systems, like for instance, there's ferromagnets or these magnetic materials, so you have the same counting, right? Like, so you have spins, if you want, or spin variables in a L by L lattice, and then if you do the same counting I was doing for the images, you get that the space of configuration has the same system size, basically 2 to the L by L. And so the commonality here is that both machine learning systems and systems of interest in statistical mechanics and quantum physics share this high dimensionality. In machine learning, this is called the curse of dimensionality, and we also experience it in quantum physics. There's also the type of objects or mathematical objects that we're interested in. So in physics, we're interested in the so-called Boltzmann distribution, which describes the equilibrium properties of these systems, and it's given by this expression here, which is basically assigning probability to any of these configurations or these spins. And whereas in machine learning, people are interested in understanding what is the distribution underlying, like say, images in like for instance, handwritten digits and so on. And so that's the commonality. We're basically interested in the same objects. It's just that they're applied to different systems. And in this case, is statistical mechanics, and then the other one is probability of finding or estimating the probability of an image. So that's the second one. Third one that is very, very important is what are the correlations in the data or in the systems that we're studying and the symmetries. And what I argue is that there's a lot of similarities between the correlations in the data that we are interested in machine learning, but also in physical systems like in statistical mechanics and quantum physics. And they have strikingly similar structure. And a prominent example is the so-called critical correlations, and these correlations appear in natural language, natural images, and even music, and all of which exhibit power law decaying correlations that are identical or that have mathematical structure similar to physical systems tuned at a critical point. For instance, when you boil water and at the boiling point, the system develops correlations that are very similar to what you find in natural images and natural language. And again, this is about correlations, but also symmetries are important, like translational, rotation, reflection symmetries, and other symmetries. And these are important because the use of these symmetries and understanding of correlation enriches our understanding of quantum systems and statistical mechanics, but also they improve the sample complexity and convergence of the machine learning algorithms in computer vision and natural language processing and so on. And so, I guess what I want to argue is that these correlations are beyond just mere resemblance, and so we started applying these ideas in machine learning and in physics. So one of the most simple ones is you can start thinking about idea of classifying phases of matter according or using machine learning ideas, which we explore very much like what you do with like this handwritten digit classification. You can then apply the same ideas to the different phases of matter that you see in an experiment, for instance, in a ferromagnet versus a high temperature phase. And so we explored this in a paper a few years ago. So we successfully applied all those ideas in several different models, like the Ising model, and on different lattices and so on. And we observed that these models successfully classify these phases of matter on average. And so this generated a lot of excitement and attention in the community, in condensed matter physics and so on. Then this was more importantly applied in experimental physics, so where people identified quantum phase transitions using artificial neural networks on experimental data, which is kind of like what we envisioned would happen, and so it was very exciting. The other thing that is very exciting to me is neural network quantum states, which is, if you want, representing quantum many-body systems or quantum many-body wave functions in terms of neural networks, which is a topic that has been around for a while, even since the 1997 during the AI winter. People were already thinking about it, and then we came up with this way of representing ground states of many-body systems using neural nets also a few years ago. So why is this important? Because I mean, using neural network as a quantum state is important, for instance, for the solution of problems in quantum chemistry, chemical engineering, and we're starting to see this paper, this deep neural network solution of the Schrödinger equation was published actually yesterday. We've understand how to benchmark quantum computers and quantum devices using generative models and material science and discovery, and so on. And so with the outlook, and what I wanted to convey is that modern machine learning techniques have started to spread through the landscape of quantum matter and research in quantum many-body physics. And we think there are a lot of opportunities for machine learning techniques and ideas, as well as the research culture that is so interesting in machine learning that I think and I believe can spark new ideas and new concepts in the field of quantum physics. And finally, I believe it's a privileged time for quantum system research due to these opportunities that are arising from artificial intelligence and quantum computing. And with that, I'd like to conclude. Thank you.
Great, thank you so much, Juan. That excellent presentation. I have one question quickly, and it's just maybe a little bit simple compared to the presentation, but I'm really interested to know your thoughts about, like, when we see all of these kind of natural similarities between data from different modalities in different domains, is this something that has a theoretical underpinning that we should expect?
So this is not quite formalized yet, I think, but ultimately the data sets that we use in machine learning, they come from physical processes, right? Like when you take a picture, this is basically recording something that is physically happening. And I think the origin or the commonality is because the data that we use as information that comes from physical systems. The same is true also for natural language and so on. So it's all based on physical communication and so on. So I think the origin is just because, or the commonality arises because all this data is physical, right? And then all this exponential explosion is just an illusion that we create when we're trying to understand this using mathematics. But ultimately, the systems have some simplicity built in, and I think this is common in physics and in the data sets that we use in machine learning.
Certainly, thank you so much, Juan. All right, now it's time for our final speaker, and this will be Nicolas Schoellig. Nicolas is an associate professor at the University of Toronto Institute for Aerospace Studies, where she heads the Dynamic Systems Lab. She's also an associate director of the Center for Aerial Robotics Research and Education at the University of Toronto. With her team, she conducts research at the interface of robotics, controls, and machine learning. Angela, I'll pass it over to you. Thank you.
Okay, can you all hear me?
Yes.
Okay. Welcome, everybody. It's a pleasure to speak to you. My team works on machine learning techniques for mobile robots. And in this talk, I want to highlight that there are certain components when we do machine learning for robots that are different to traditional machine learning. In particular, around safety, data efficiency, and fast adaptation. But let me give you a glimpse what our work looks like. So if you come to our lab, you see real robots moving all the time. So we have, 25 small flying vehicles flying in coordination. We use that in applications for building monitoring. We also fly outdoors based on vision only in winds up to 28 kilometers per hour. And we use vision as a fallback if GPS fails. Here we fly in a mine. And we also have some projects where we move self-driving vehicles in off-road conditions and on the road. So this is a self-driving competition we are participating in, and we have won the last 2 years. The vehicle is completely autonomous. And this is our latest robot, a mobile platform with a robot arm. So our research is really driven by the vision that robots will enter our roads, fly in our skies, support us in our daily tasks, including cooking, and collaborate with us in the workplace. And all of these applications, what they have in common is that from what we have right now in robotics, we have to enable robots now to deal with increasingly complex and unpredictable environments. And in these environments, robots still have to actively make decisions, for example, what move to do next. And we expect them to do that in a safe and understandable manner. I also want to highlight that we recently published a white paper about how robots could be used in a pandemic as COVID, and how they are currently used during the pandemic. And it has been also these kind of applications, such as cleaning in a supermarket, require a lot of intelligence and dealing with unknown and changing situations. So in this talk, I want to give you a little glimpse into what type of characteristics we have to deal with if robots learn in the real world. So typically, if we think about a robot, we think about input and output. So a robot is a robot because we can move it in a way we want. So we can send inputs to the robot, and then we can observe outputs, which are the, for example, the robot's movement. But in the real world, and especially in the applications I highlighted, the behavior of the robot is hard to predict. And sometimes we write it down in equations like this. It's not as important that you understand the details, but there's usually a common component that we know ahead of time, or this can come from like a physics model. So we roughly know how a self-driving car moves on the road. This is what I call an a priori model, but there are many things that we don't know how they affect the robot's movement, or we just don't know that those can happen. So for example, we can have icy roads, snow on the road, lots of rain, and this will affect the robot's behavior on the road. And these are things that we don't know. So traditionally, there's no machine learning to make a robot accomplish a task. So typically what we do is we do this kind of a feedback loop. And we design what I call here the baseline controller purely based on our a priori model. So our a priori understanding of how the robot moves. And we kind of ignore the unknown parts. And if these unknown parts are not significant, this works really well. And it works really well in many situations. For example, here's another video where we coordinate the motion of 10 vehicles as they move through this hula hoop. And there's no machine learning at all. And this works. And it works purely based on our prior understanding how these flying vehicles work. And it works despite their quite complicated aerodynamic effects. But there's limits to this approach. So if we want a flying vehicle to do a really fast slalom maneuver, what we see is that if blue is the slalom trajectory we want to follow, and we use the proposed approach, what we see is a large repetitive error. So whenever we do the task, we don't do it well. And so what you can do instead, you can try to learn this offset. It's a systematic error. So you can imagine that you somehow can learn this and compensate for it. And I'll just show you So, and we do this just as a block. We rely on this baseline system that we had before, and we just add a learning block in front of that. And so here's how that works. So the vehicle learns above the poles, and it takes the information from a previous run and updates its strategy. We can do this task really well. And we can also learn from scratch another task. But this one is the learned result after training again. So we learn in this example, we learn one specific task through iteration, something similar to what humans do. If you want to play a piece of music, you practice a lot of times the same piece of music, and at some point you can do it well. But robots should do many different tasks. And so we were wondering, can we learn something a bit more complicated that allows us to do an arbitrary number of tasks? And so we learned this new block that has this feedback at the bottom. And so then we could demonstrate that we can now fly any hand-drawn trajectory. So you could come to the lab, draw a trajectory on a tablet, and we can fly it. And with the learning block, we can improve the performance of the robot by 62%. That's already really good. I still want to highlight, we still have this underlying standard controller, which makes the learning task much easier and allows us to learn much faster. But this learning block at the beginning, that's now a deep neural network in this case. We use a very similar approach also to do a very challenging task, such as catching a ball with a mobile manipulator, where you have to be extremely accurate to catch the ball. And you can throw this ball from any direction and the robot can catch it. So finally, another key property of robotics is that we have, as they learn in the real world, we have to guarantee that they stay safe. And here you see this in the red box. It's kind of what it means is we need the robot, for example, a self-driving vehicle, we want it to stay in its own lane. And we also know that there are limits to the acceleration of a car and deceleration of a car. So this is kind of the two constraints that we have. And so how can we guarantee that a robot, as it operates in the real world, for example, as it cleans your house, it gets better and better at doing the task while never jeopardizing, crashing into walls or, destroying anything in the environment. And so for that, one approach that we did, and that was pretty novel at the time and kind of led to a whole spark in research into this direction, is we basically say initially we don't know much about the environment and the robot, and we have large uncertainties, which is kind of this light blue envelope. So for a given function, we have lots of uncertainty, and initially we are very careful, and we make sure we operate the robot such that no matter what the uncertainty is, we are safe. But then as we gather more data and the robot moves in the real world, this blue uncertainty envelope shrinks and we get more and more certain, and the robot gets better and better at doing the task. And so here's an example. So here the robot moves without learning and it hits these orange pylons because our initial model is not great. But then as it learns, it can safely drive through those pylons while continuously estimating the uncertainty. So it never is perfectly certain about its behavior, but with more data, we get more certain. Is this pink envelope here in the plot. So we can safely get better at doing a task. So overall, my research lab looks at robot learning, and there are many key characteristics that are different for robotics than they are for standard machine learning problems. One is non-static conditions matter. So I've shown you the behavior of the robot is uncertain and it can change. So weather conditions can change very quickly, and we need to have architectures and learning schemes that quickly react to sudden changes and guarantee that nothing harmful happens. Safety matters, so we really need to make sure a robot doesn't destroy itself or the environment. And learning architecture really matters. So a robot is an extremely complicated system, and decisions are made at very different time scales. So for a flying vehicle, the most low-level decisions are made 1,000 times per second. And so enabling learning algorithms there is very difficult and may not make sense, but we could employ it at a very higher level, as I showed you, outside of the loop. And so by also strategically choosing this learning architecture, we can be very data efficient, and we can even show that different robots can learn from each other. So overall, my group works on learning theory for robotics. For example, we have a very well-cited paper on safe model-based reinforcement learning with stability guarantees, a very foundational problem on safe reinforcement learning. We heavily rely on robot experiments to really test our algorithms with the goal to ultimately translate this into new robotics applications and enhance the skills of robots. And so if you want to learn more, all the latest papers are on our webpage, dinsyslab.org. Thank you.
Thank you so much, Angela. I particularly enjoyed seeing so many connections between this talk and some of the others today. Unfortunately, we are at time and don't have any time for questions, but I would encourage anybody who's still in the audience that does have questions to reach out to Angela or to any of our other speakers with their questions. And I think with that, we will conclude the session. I wish I were going into my PhD again, but then I would have a really hard time choosing between the 4 labs that gave us presentations today. And thank you very much, and I hope you enjoy the rest of this day.